let's talk about, we take Ram's algorithm and put it on a system. So by the way, let me introduce myself before I start. Ashish Shah on the Haseeb's team on the product management side, but I was an engineer and back then. So we'll talk about how you take this algorithm and implement it on a system. And we'll also talk about some of the TCP stuff. So I will go quickly over some of the slides. This is the only marketing slide I have, which is you take the algorithm and put it on a system. What do you get? You already saw you get 10 gig of throughput. The other thing you get is fat connections, 1 gig per flow, right? We talked about that a little bit, that with branch, typically you get megabits per second, that's good enough. But here you need fewer connections to fill up the pipe. So we can scale each connection to 1 gig. And latency, you never heard the number, but on an average, the port-to-port latency, so in and out, is the 50 microsecond versus tens of milliseconds. So that's the reason you can put us in line for replication path. Everything else is just derived and just marketing, so I'll skip that. So 3 things we do as a part of our system. So I'm going to again talk about the system as a whole using deduplication and TCP optimization. So first thing we do is control, which is select what packets or what flows you want to deduplicate or optimize and provide quality of service. Quality of service through Broadcom switch, but also at the TCP level. We'll talk about that, including minimum bandwidth guarantee, maximum caps, weighted round robin, the whole suite of QoS. And then you do the TCP optimization, which is the TCP part, the TCP proxy. And the third is the reduction. Now, reduction is not just deduplication. He hinted at some of a key thing about repeat byte suppression. And so because we do it in hardware, as the bits come in, we take away the repeated zeros or ones as we build the packet in hardware. Then we do the dedupe. We get smaller fragments, if you will, coalesce them, compress them further through gzip. And then it goes out. So it's a combination of 3 different things that we do for reduction. Okay, so next, how does it work? And again, we saw in Ram's slide deck that x86-based platforms have inherent limitation through serialization and memory synchronization. So I won't spend any time on that. We did a different approach. Merchant silicon, yes, but also a distributed system. It's a pipeline system as we'll see it. So we have a Broadcom switch. We have a Cavium network.
Look, no x86.
There you go.
This is the Broadcom. This is the FPGA. You know.
And a Cavium. So we have Broadcom, Cavium, and FPGA, and they do 3 different things. And these are parallel. It's a pipeline system, and let me show you how. So, by the way, the board looks identical to what my next block diagram is. You have a control plane. This is where the management, etc., happens. You have the switch plane. That's a Broadcom. Then you have the data plane. That's where you have your Caviums and your FPGA. So as the packets come in, they hit the switch. It's a 160 gig switch. We have 4, by the way, we have 4 10 gig interfaces plus 2 for ISLs. So 4 10 gig, we can take 40 gig of traffic. We optimize up to 10 gig, the rest would go bypass. And so there is no bottleneck on the system because it's a switch. The traffic in the orange that I'm showing is bypass because the policy says don't accelerate that flow. So it just flows through. It's a bridge, right? The rest of the traffic shown in green and blue goes up the stack. It's not really stack. It's the pipeline architecture. It goes to the Cavium. To your point, Ivan, this is where we terminate the LAN connection of TCP. So we terminate the local connection. Then the packets flow into, and we implement some buffering based on QoS. Because QoS has to be implemented not just at the switch level, but also the TCP level. Because if there is congestion, just switch level QoS won't be sufficient. So we do what we call it L4 level QoS. Then the packets go up to the FPGA. This is where the magic of repeat byte suppression, deduplication, and compression happens. Flows down into the network processors again. This is where the TCP, the WAN side of TCP happens. This is where we do the magic with congestion control, aggressive congestion control. We'll talk about that. And that's also QoS aware. So we make sure that if the WAN link is congested, the traffic that we push is in proportion to the QoS.
I'm guessing by QoS you mean DSCP markings and stuff.
No, actually it's local. So in terms of if there is congestion, which application should be throttled back? So it's about weighted round robin. So it's more about weighted bandwidth management, flow bandwidth management.
So it's per flow weight per QoS.
Yes.
Yes. Okay. Yeah. So the challenge with a proxy is that. Yeah, so basically what happens is, if I do QoS at layer 2, so I will have my queues at layer 2, and then I proxy everything. The minute you proxy everything and your plan is sufficiently long enough, which it is, everybody be equal, right? So at the level, at the buffer level, you have to make sure that the buffers at TCP level match your QoS policies. So if I have, let's say the customer wants is they say, what, I want 80% of my link to be replication and 20% to be backup. If you have proxy, it's very hard to do because everybody equal. So we have to actually manage the buffers at layer 4 to make sure that actually happens. Because think of it, if you think through it, if you have retransmissions, everybody's equal, right? So we have to make sure that happens in the network processors. And that is a very unique feature. Nobody does that.
Do you usually experience the congestion egressing towards the LAN, I would think?
No.
Egressing towards the WAN.
Towards the WAN on this side. Yeah.
Isn't a typical deployment a 10 gig interface on both sides?
That's correct. So basically what will happen is...
You can't take more than 10 gig in, you would never be congested going out.
So we will not be the congestion point, and the congestion point is not directly downstream of us. The congestion point is at the LAN-WAN edge. But we are not going to be directly connected to the LAN edge. So let's say we're sitting right behind a 7K, which is connected to an ASR. Right? Now that ASR might feel some congestion, or not congestion because the link may be, let's say the link is an OC48, right? So let's take an example. OC48 going out, or whatever, 2 gigabit MPLS. But what the customer wants is to be able to push, let's say 10 gig on an OC48, right? So we'll set up our box, at the, we'll configure QoS such that we can receive up to 10 gig and push out 2.54.
So you are doing, you actually have to do traffic shaping on the output ports.
Yes.
Because you have like DSL-like issue.
Yes.
Congestion is downstream from
Yes.
Yeah.
Yes.
So now the interesting thing is the following. The question is, you can drop packets to ship, or you can actually manage a window.
Yeah,
So we manage windows. We don't
You can't drop because then you get into retransmission.
Yes,
You have to ship
exactly.
unpolice.
Exactly.
Whoa. Not
Okay.
necessarily. Depends how you drop it.
No, it's always gonna be dropped.
You could theoretically do ECN, right?
No, where ECN, well,
I said
where is that?
Marco, we had academic versus effective.
Yes.
Yeah.
So the way we manage it is that this side, so we configure, if you know the downstream link is 2 gig, you can put a bottleneck of 2 gig through configuration. So what we do is that this guy will push back through the system if it's hitting the congestion, and then the LAN side TCP can reduce the window appropriately to slow down the server.
Yeah, but you still need to match your output to what ASR is doing on the
Yes.
Sure.
output.
Yes. Yes.
So that the ASR has to give the
You basically have to
The DMS.
optimize
Yes.
so that you
higher
can-
priority
Yes.
than anything
Yes.
else.
Potentially.
And you basically let the ASR do first in, first out, and not
Correct.
implement any of the
So-
queuing or.
So very
No,
typical.
they have to put their traffic in high priority queue.
We can. So for typically what will happen is
on their box, but
No, on ASR.
On the outgoing link.
Otherwise, they can't manage the QoS.
if you want. So what some
Okay.
So basically, the TCP session will reset.
Yes. Effectively. If you get multiple of those.
Yeah, it depends on the scenario, but it basically what will happen is let's say the client send a packet, which was acknowledged. So let's set that aside. And then let's say there's a second packet that goes through as well, right? If that goes around the DMS, it goes straight to the other server on the other side. The sequence number that the server is expecting is not what it'll get, because previously it was getting it from us. So it'll say, I don't know this packet.
So
It'll ignore
you
the
are
packet.
playing with sequence.
They are.
We change it the first time around. So when the connection is being set up,
Yeah?
we flip it. We basically shift
like
it.
everyone else.
Yeah,
Okay.
Yeah, that we don't have a
Basically
choice.
to prevent this failure.
Yes.
scenario.
Yeah.
So the choice there is if we were a non-transparent solution, then there's no need to do this. If you actually were to tunnel trap,
Yeah.
so the reason why people do this is because if you actually miss the other guy, we don't want the server to get corrupted.
Yeah.
Yes.
And the other question was, how does the other DMS detect that this has been accelerated?
Options, TCP options,
TCP options on the scene.
Yes.
Thank you.
and going forward as well.
Yeah.
So what happens if there is something in the cloud there that doesn't like the options that
You reconfigure your firewall, Marco.
I'm not talking about the firewall, I'm talking about something that you don't have access to.
So most firewalls are okay with that. I mean, the options that we use, we haven't really found an issue. If you really have a big issue, we have a tunneling option as well.
Yeah, okay.
So yeah, we
So-
have a tunneling option.
So worst case, look, I mean, the idea is as a vendor, we can't say this is how you do it and there's no other option. Go figure out your firewall.
Well, maybe
We
you
have
should
another
talk
option.
to VMware.
Yeah, let's do that.
That's exactly what they do.
Let's do that.
So but you had one more question, Chris. Yes.
Well, so, I mean, I understand the packet that goes around is rejected
Yeah.
because the sequence number is way out of the window. But I'm still worried about the TCP segment that has been acknowledged and never gets delivered.
Let me respond to that question with a question, if
Okay.
I may.
I guess the flow is dead.
So this is, so flow is dead, but the question is somebody's acknowledged the packet. So what happens with the application?
Well, somebody's acknowledged the packet, but it was a lie.
Yes, it was a lie. So let me ask another question.
Okay.
Let's say you have a Linux box.
Yeah.
Okay, TCP runs in the kernel,
Yeah.
right? TCP acknowledges the packet. Application, you have to send the packet up the socket to the application. Let's say before the socket read is done, the server crashes. What happens? There's no solution.
Same problem.
So the right way to solve this problem is, and not most, all applications do, is they have application level acknowledgements. So that's, I mean, FTP to some extent does not, but even there you have a file, I mean, you can have a file level checksum.
FTP checks the file size.
Yeah, file level checksum and stuff like that, right? So that's the idea there. I mean, if you have
file copy will do the same thing.
Some really, I mean,
You get
way back when, you know, if you had like, you just open a socket and blindly write stuff. So that, I mean, you know, in college we used to do these things, but really apps don't do that because there is no, you cannot rely on the kernel to accept packets, because how do you know? Just because the kernel acknowledged something doesn't mean the socket got it and doesn't mean the application got it. So you have to solve that problem some other way, and we just piggyback on that solution.
Gotcha. TCP options for detection of DMS boxes, how does it behave if there are 3 in the path?
So typically there aren't because of the deployment. I mean, we can control that with the customer, but we have basically the way it works is I need to use the whiteboard, but the idea is that if we see an option on the SYN and then we send it forward so the receiver, the guy that's closer to the server, if it sees a SYN-ACK without an option, it knows that it is closest to the endpoint. And if anybody in the path sees a SYN-ACK with an option, it thinks I'm in the middle, so I shouldn't do anything.
Okay, so it establishes through the
yeah, basically the guys who are closest to the client on the server, they should be doing all the work.
This is what you want. Yeah.
All right, so I know we are running out of time, so I'll just quickly some deployment considerations we've seen. One common problem is routing asymmetry, which is a multiple WAN links.
So you're convinced?
No.
Wait for the beers.
Did you bring a checkbook or?
Wait for the beers. No. So you go have different WAN links, right? If the same DMS is not handling both ends of the flow, then you can't accelerate, right? So there are 3 solutions. Make sure the DMS is placed such that it sees all the links, not always possible. Other is we do link state sharing between DMSs. And third is tunneling. So if you do end-to-end tunnel, you'll guarantee it goes to the location. So that brings to the next slide on tunneling, that while most common deployments are non-tunnel transparent, some customers want to use tunnels for 2 reasons. One is UDP. UDP, there is no connection. You have to use tunnel. So that's what you do. On top of UDP, for loss mitigation, we have a parity-based checking mechanism we call RPR that can be used if you want to do some loss mitigation. The other tunnel use case is avoiding routing asymmetries. Still proxy, but the proxy TCP connection, the middle connection, is on top of a tunnel. So it's a GRE tunnel or a UDP tunnel.
So if you're using tunnels, you can actually make UDP lossless in the middle.
Well, the tunnel is a UDP tunnel, but if the payload is UDP, where do you put the ACKs? You want to have a TCP tunnel, right? Yeah.
So you don't do that?
No, we don't do that. We don't do TCP.
In theory, we could. The challenge is most applications that are UDP. I mean, mostly the only real one is right. That's there.
So actually,
so
VPlex,
it's not practical. Right? It's possible. It's not practical.
Yes.
So EMC VPlex uses something called UDT, which is a application protocol on top of UDP, which has its own reliability built in. So that's how this comes in.
Yeah. So what we find is a parity check for UDP is pretty good for most applications. We call it RPR. What does that stand for? Resilient Packet Recovery.
Has EMC blessed this as a valid solution?
Yeah, so we'll be announcing that soon. I can share more.
It's in progress.
Yes.
It's basically the last step is.
Because EMC likes to bless everything and extort customers.
Yes.
I see that you have not implemented a solution.
We see this as a non-standard solution.
All right.
But on the other hand, EMC uses its own protocol on top of UDP.
Right.
That means that you can't accelerate that.
So
we have.
Go ahead.
You have to understand to do that.
You can deduct, but you can't accelerate.
Correct.
Okay.
Correct. It's right now the acceleration part is for TCP.
Yeah.
Yes.
So
it's a deduplication.
The application, the protocol they call it UDT, it's a very aggressive version of TCP. So what they've done is they took UDP, they added acknowledgements to it, they added aggressiveness to us.
Yes.
It's TCP.
Yeah.
So eventually, my theory is that eventually they'll say, let's just use TCP and let somebody else worry about the protocol stuff.
Okay. So you tell the EMC guys to use iSCSI.
All right, so this is the deployment option. I think we touched upon something. So typically it's between a switch and a router. Inline, you can do HA as well, or out of path through policy-based routing on a router, or filter-based forwarding with Juniper.
If you do HA, would those be two parallel links between the switch and the
No,
router?
so this is just one. This is active. HA is active passive for us.
Okay.
Yes. But
you would have two interfaces on the switch, two interfaces on the router, and
If
one of
you-
them would be down.
yes, through VRRP, yes.
Or we can do it on our box. Basically, we can kill the port, or we can basically.
Okay, so
Yeah.
one of the connections would be down.
Correct.
It-
No loops.
Yeah.
Yes. And for out of path, this is a very common deployment as well, where you do not just
PBR.
active passive PBR, but you can also do flow-based load balancing. So we have IP SLA tracking or next health checking, and you can do multiple of these boxes in parallel and do flow-based load balancing. And if one of them dies, the others can take over. So we have a customer who wants to use 4 of these, and you can do that in parallel.
4 of these boxes,
10
and 10 gig each.
Okay.
And this is a common dual router deployment. So here, the dashed line that you see is this for the state sharing through ISL. So if you see packets going out on one link, coming back on the other link, well, we can share the TCP state information to make sure that we can still accelerate an asymmetric TCP configuration. And this is just out of path version.
Is it?
This, yes. So what happens is
So how do the packets flow in this one?
through PBR. So
It's back through the same interface?
no, yes. So if it goes out this way,
Yeah?
doesn't matter which. Let's say this was a switch that accelerated this flow
Yeah.
and went out that way.
Yeah.
Regardless of which way it comes back,
Mhm.
the two routers will make sure it goes back to the same switch, and then back up.
So the next
so
step.
both interfaces are in and out.
Yes. Well, yeah. There's actually two interfaces, LAN and
Oh, yeah.
WAN. We are just showing logically. Yes.
I think that's what he was
Yes.
asking.
Yes. There are two. There's a LAN interface and a
There
WAN.
was
Yeah.
something missing in that
Yes.
picture.
It's a
Because some people
two
have
logical
logical
interfaces.
Yes, logical link.
Yes. So that was it. What I wanted to share. Any questions before we go to the final summary?
All good?
I think it's time to go to the final summary.
Yes, actually, that's well. We already checked back in the demo.
Yeah.
It's good, right? So I hope you guys had a good time at least.
Yeah.
Right, so very quickly, what we talked about today. So look, we call ourselves the first and only WAN optimization company that solves the big traffic problem, which is what exists between data centers. We talked about the patented technology. That's what Ram talked about. He walked you guys through how we don't have the bottlenecks that their traditional applications do, how we solve the memory I/O issues, etc. We talked about the system architecture. We showed you the box. We are merchant silicon based, very similar to like a Palo Alto Networks, if you will, right? How they have designed the system is very similar to what we do. And as a company, we really feel that that's the right approach to building high-speed systems. And we'll talk, if you guys have a few more minutes, we have a few more questions after we shut down about what we're working on next and how we think that's actually even cooler. We talked about the TCP work that Ashish talked about that, how we are unique in how we manage TCP connections, and at the same time try to give customers as much flexibility as possible. So TCP, UDP, tunnel, asymmetry, whatever. Our goal as a vendor is to make sure we support all these possible scenarios. And of course, we looked at the demo. So you guys saw the demo, 28 minutes versus 25 hours. Right, so huge difference. So with that, if you don't have any questions, by the way.
No.
Cool, awesome. So with that, let's close for the day. Thank you guys for your time. We had a lot of fun. Hopefully you had too. And let's continue the conversation right after.
All right.
Thank you very
Very
much.
good. Thank you.